David Humphreys. Dr. David serves as the Director of MFE Operations and Innovations at General Atomics with 40 years of experience in fusion research. Dr. Humphreys has led several international efforts to develop control solutions for ITER fusion power plants and other long pulse superconducting magnets. He received the 2017 IEEE NPSS Fusion Technology Award for contributions to plasma control and is Fellow of American Physical Society. Dr. David Humphreys.
Can you hear me? Let me first acknowledge that I'm going to be showing some results from people in the D3D team from many institutions, from Princeton, from Columbia, from MIT, as well as people who work in AI and experimental science on the machine from General Atomics. A lot of what I'm going to say is derived from a workshop that Department of Energy held between Fusion Energy Sciences and the Advanced Scientific Computing Office in 2019. But this talk, the talk that summarizes the report, is actually included in these slides after what I'm going to show you. So I encourage everyone to commit that to memory and learn all about our workshop. It is very, very relevant still to this day, which goes to the point that there's still a lot to do in the AI space. So with that, I'd like to pivot a little bit from what Steve and Richard told you to reorient you to a little bit of a different view of tokamaks. Power plants will be very different from our physics experiments, but even now, there is a sort of a physics perspective of tokamaks. They're very pretty, they have curved spaces, and they're complicated, and that makes them interesting. But of course, there's an engineering view in a sense, and I'm being a little bit glib about this, but bear with me for a moment, where you'd like things to be very simple, sharp corners, at least where that makes modeling easy, and you can handle this thing as an operational device. But more interesting perspective from my point of view is the control and operations view. That is that tokamak power plants and even our present devices, especially things like D3D that are in this high performance space, are a lot more like high performance aircraft. So let me tell you what I mean by that. So here's your canonical power plant. A high performance experiment like D3D even is in this space. Many requirements are mission critical. That is, if you make a mistake, things get damaged, and you destroy your availability. High performance and reliability are required at the same time, and these are often in tension. You have to be able to operate these devices first time with minimal tuning. And as I'm going through this, I'm talking about both these kinds of things and these kinds of things, the ones you sell to a customer. That means operating first time with minimal tuning means you deploy it, you have to, take things out of the shrink wrapping. You can do a little bit of commissioning, but it has to run. You don't get 10 years to make your system work, collect a lot of data, validate everything, and then your customer starts to get money from power on the grid. You have to certify, therefore, that high confidence performance. You have to give them some assurance of the lifetime so they can invest in this with their eyes open. Interestingly, these systems and these systems have comparable control complexity in various metrics, like thousands of sensors, hundreds of control parameters, maybe a dozen key instabilities you have to deal with, more with these than with those, more with these depending on your configuration choices, and like hundreds of actuators. But in fact, it's even more interesting than that because these things are a lot like damaged F-15s. What do I mean by that? I'm not sure how many of you have seen this fantastic event in 1983. I'm sure several of you weren't born then, but there was an incredible event where an Israeli Air Force F-15 lost an entire wing in a mid-air collision during a training mission over the desert in '83. And it continued flying, and it landed safely. No wing. So this is a tribute to the design of the F-15, its lifting body characteristics, looking at you, Kenji, and the control system, which was one of the first self-correcting, self-adjusting control systems, and it could configure for the new flight characteristics in real time. Also, the pilot was incredible. Israeli pilots, say no more. So you have to have extremely effective fault robustness and management. You need to prevent faults. You need to see them coming and not even get there. These planes actually were the first fighter aircraft to do that. And then in real time, you have to adapt to whatever kinds of faults are happening. Ideally, correct them in real time. This is a little hard to correct. And you have to operate with very limited observability and controllability. Now, Richard referred to this briefly, but I'm just going to give you a gestalt sense of this. This is the D3D control system, at least a summary of a fairly small part, actually, of our controls. They're actually 10 times this size, but these are kind of the high throw weight ones. And don't look at the details. There are lots of things being controlled. There are lots of actuators, lots of measurements. But in a reactor, as Richard mentioned, you're not going to be able to directly measure the quantities you would really like to. D3D has this vast diagnostic set. You will get maybe 10% of that. Also, the direct control of many of these features will be impossible in a reactor. You have to control things indirectly or with very low levels of control authority. Your control gradient, if you will, is like small, right? So you also have to operate near instability boundaries. This is starting to get a little bit concerning, right? You need a very, very high-performing system to deal with all these things at once. And at the same time, you have to certify the performance. Now, to be fair, this is what fighter aircraft do. This is what designs do. So you're going to miss all of these kinds of functionalities and just be left with a few in a reactor. Okay, so with that said, let's look at what operations looks like in a tokamak for both experimental systems and a power plant. This will give you a sense of the things that I want to focus on for AI applications, and that is this operational space. So basically, you start with some system that's not functioning right now because either you shut it down a while ago or you're first time on the grid, right? You commission your systems, your plant systems, you plan and prep for startup, you actually start it up, and then you run. Some of these configurations we imagine to be pulsed as you're producing power. They go on, they go off, you go on, they go off. Some of them will be steady state. As both Steve and Richard said, we don't really know what's going to be the winning configuration for an actual economic power plant. That's a pretty fundamental thing not to know. But at any rate, this operational space goes on for maybe months, maybe 11 months, and then you shut down for maintenance and repair and refurb just like a fission reactor. And then maybe you're going to upgrade stuff, maybe every 10 years, and then you do this again. Okay, so there are a lot of these functions that you're going to have to do, commissioning, monitoring of faults, maintenance, repair, and during the operations, even more, and even more challenging because you got to know your planning and operational space. If things are varying on your plant, you need to take those into account. This is why data collection and incorporation into active models, tracking that in real time if you can, is important. You're going to do commissioning with plasma, that is in the initial operations in this startup part. You'll need real-time control algorithms, you need fault prediction, detection, prevention, and then you'll need to debug things as you're going. In the AI space, a lot of tools that are available can help this process. You can have models that help you with your commissioning design and executing it. You can use fault monitors you've designed from data-driven solutions and anomaly detectors. You can have simulations that are either very, very accurate, digital twin type that ingest real-time data, surrogate models for accelerating those simulations. And then in operations, many of these same tools can be used. You can use some of these digital twin tools for scenario and operations optimization, for monitoring faster than real-time controllers, et cetera. So one of the things I'd like to highlight, looking back at the way we're like a high-performance fighter plane, is that you need high performance and reliability in all of these applications. So if you're going to use data-driven or hybrid data and physics-driven models, you've got to always be looking at that as the output. You need error tolerance in your models with UQ that's intrinsic to the process. And of course, you need to somehow support successful first-time operations. You need a workflow and an application of these tools that get you there. And then, of course, performance certification, whatever the regulator needs, fine. The Nuclear Regulatory Commission right now seems to think fusion reactors are more like an accelerator. That will probably change. But in any event, the customer is going to need some level of certification to know that their investment is well-founded. All right, so I'm going to give you a quick tour of some things we've done in the space, but I'm going to cut this a bit short. This is one of the general kinds of approaches that we take to predictors so we can look ahead to instabilities and prevent them. So it's a model of many, many types of things we must solve for tokamaks and many configurations, in fact, to be successful. So there's a controllability metric, and you need to stay in the safe zone here away from the death zone in real time. And often these systems have excursions, disturbances, exogenous variables that drive you out here. So you have to quantify the uncertainty in that with enough statistics so that that doesn't happen. So this is an example of something we deployed with a machine learning-based surrogate model and analysis of our latent space for an instability called the vertical instability. If you stretch the plasma this way, it tends to be unstable to shift up and down. So we have to actively control this. And so we're monitoring the controllability metric, which is the growth rate for the instability. If you don't do anything, the red curve happens, you lose the plasma. This is the plasma current, so the plasma current goes to zero, gone. Not a good result. But if you control this parameter and make sure that that excursion doesn't happen, you can stay in here, the discharge goes all the way out, and you're good. So a similar kind of thing, you've now seen two versions of this with Eggum and Coleman's work from Princeton working on D3D with this terribility limit. So there is a very, very problematic instability that we still have not solved, but machine learning is getting us very, very close to a solution. The real trick is going to be how do you transfer that to a reactor? So transferability is going to be a theme I'm going to come back to. But you can see again, here's the invisible stability limit. And if you don't control it, the black line happens, plasma goes away. But if you do control it, plasma stays. So again and again, these things are already transformational in our experimental operations. I wanted to highlight this one, the so-called density limit for plasmas. We thought that if you increase your density, you reach some hard limit where the plasma, again, just disrupts. It goes away rapidly. There's a simple scaling called the Greenwald limit people used, and you can see here the probability density distribution for stable and unstable, highly coupled, big covariance there. But if you do an interpretable machine learning analysis of the data with physics quantities and the input, you find it's not density, in fact. It's collisionality, in fact, the collision frequency, and this beta quantity that Steve was telling you about, but the edge beta quantity. So it's a very subtle bunch of physics quantities that are far better at separating the stable and unstable states. And the ROC curve, this is absolutely beautiful on this. AUC is, close to like 0.97. So it's amazing what kind of performance you get with this. And scientific discovery, learning what the underlying physics is so you can extrapolate that to a reactor. All right, so let me just bring this all together, hopefully quickly. So there are a lot of areas. I've been focusing on operational things, but you heard mentions of surrogate models to accelerate computation, which is huge, huge. That is something we critically need, as Steve pointed out. This could be, by itself, transformational if you just brought the capabilities to systematically execute the process he was talking about. Digital twins that are properly informed by data, and then all these operational real-time controllers, event predictors, solutions that we need. On the outputs, it's equally critical for us to do this scientific discovery so we can extrapolate to things we've not seen before, not built before. And being able to transfer models to those configurations is equally important. I'm going to skip this. So you heard something about the Fusion Data Platform, which is the Department of Energy's supported project that General Atomics is running, but with many institutions around the US and the world. Basically, it's a federated data management platform for the entire fusion community to try to get our data collected on present devices and simulations into a single space with a common metadata framework. Richard mentioned we're building on OLCF. We're building on existing systems that people are familiar with at CERN and other places. We support curation and marshaling and some key applications. Eventually, we expect to ingest all kinds of applications on the output layer that allow people to rapidly perform workflows. So it is a super important resource that fortunately DOE has recognized we need. And it's already on the way and running. Similarly, these digital twins are very hot in the news right now. Doing the kinds of simulations Steve showed you beautiful examples of forever. And some of those actually try to mirror the true machine. Many of them are very physics-oriented, and they don't really need the details of a lot of the operational characteristics, but the ones that we use on D3D and on other machines where we support the control around the world, we have very accurate models that ingest data constantly to validate and upgrade the as-built and as-deployed characteristics. That's the main characteristic of a digital twin that we need to now make routine everywhere. But these are also platforms that can optimize the integration of heterogeneous physics models and data-driven models, and that, of course, is critical. Okay, so here's the heart of what I wanted to get to at the end. There are fundamental advances we need in the mathematics of AI and machine learning techniques in order to really maximize the impact on fusion experiments. We have been kind of doing things ad hoc with a bunch of physicists who learn about PyTorch and like, oh, wow, I can create a model, it's fantastic, and they're super powerful. But you need very specific solutions here. You need tools to build in interpretability characteristics in your models so that you can do real scientific discovery of the type I showed you. And that's the way you're going to be able to extrapolate to a reactor you haven't built yet. Certainly haven't put on the grid and experienced all of the hair of operational deployment. Being able to integrate physics-informed and data-driven hybrid models, you probably all know, depends on this interpretability layer. The ability to connect those things needs that. And I think we need more theorems. We need more understanding of the mathematics to make it happen. Very closely related is transferability. If you're going to take these models, combine data sets, and be able to transfer the data to a brand new machine, you're going to have better theories, new approaches to validating and making these hybrid models that are transferable. UQ and performance quantification, again, it needs to be built into everything you design that's going to deployable forms, especially in mission-critical applications. When you get there, anymore, someone's going to tell you, where's your 3 nines boundary? I'm not even going to let you fly the thing unless you know that. Or at least you can convince me you have some confidence in it. High investment protection. And then related to this again is knowledge-constrained LLMs and PINNs, the whole workflow that takes physics data and can merge it. As you know, this is like holy grail, extremely hard, but that's why we're here. This is way beyond our community's abilities. All right, so to summarize, there are enormous numbers of aspects of both design, which I have not covered in any detail, but you saw pieces of in Richard and Steve's talks, that can be advanced through ML/AI. And operation I will say this now, we will not be able to operate a reactor in the reliable space, commercially interesting to a customer without these kinds of data-driven solutions with the characteristics I've talked about. Specific solutions targeted like predictors and controllers, surrogates, and digital twins. We have to not get distracted by things that are cool, but they're not on the path. They're not really going to get us to the true solutions. There are plenty of things to do that will. And every solution has got to have some level of UQ and error tolerance built in. Both sides, UQ and error tolerance on the output performance. And I think we need advances in the fundamental mathematics. I think the community needs to really engage with our problems to get the level of capability for interpretability, transferability in this certification mission. And finally, it's a bit speculative, but already we're seeing that we know a lot about the physics. I mean, Steve talked about all of this incredible theory level of very, very successful representations of plasmas. We just need to merge that with data-driven models to get to the real point. And so we need attention to that. With that, I'll close. Thank you.